Hello everyone, I am Amit Devnath and we are presenting Metropolis algorithm for XY model. So what is XY model? In XY model, each side of the lattice has a spin which can point in any direction in a plane. Mathematically, the spin at each side is described by a 2D unit vector. In absence of external magnetic field, the Hamiltonian looks like this. So now in detailed balance condition, we know that in equilibrium state, suppose mu, the net transition rate from that equilibrium state to any other state, suppose nu is 0. So we can write this equation. Finally, probability of transition mu to nu is governed by this relation exponential minus beta delta e, which we will use in the algorithm. Now, what we do in Metropolis algorithm? We randomly select a spin from the lattice, then part of its spin in any direction. Then we calculate the change in energy. If the change in energy is negative, then the we accept the new configuration. But if the change in energy is positive, then we only accept the new configuration with some probability exponential minus beta delta e, which I said earlier in the detailed balance condition. After that, we repeat the whole process again.
I have implemented this code on CuPy. Here we can see my result from CuPy and the result from sequential code are matching for two different grid size. This is the initial configuration of a 32 into 32 grid. These are the final spin configuration uh, for T equal to 0.2 Kelvin and T equal to 8 Kelvin. At low temperature, vortex and anti-vortex pair forms, and this is a quasi long range order, but at high temperature it is a disordered phase. At low temperature, the for 10 million steps and 20 to 20 grid, we have found that of magnetization is saturating to a non-zero value. This suggests that there are regions where the spins are aligned to give a non-zero contribution, but at high temperature uh, it is very small. Also, the energy is very large compared to that of energy in low temperature. Here we can see, as we vary the temperature, magnetization and energy is going through a phase transition. We have also showed the CV. From here we can found the critical temperature. These are the speed up. These are the plots. Here x-axis is in log scale. We can see for fixed number of steps, as we vary the grid size, it is speed up is increasing and got a maximum value of 394 at 5000 into 5000 grid. And for a fixed grid of 500 into 500 grid, we can see the speed up initially is increasing, but after a certain point it is saturating. Now Gaurav will take over. He will present the speed up for multi-threading and he will try to interpret the results physically.
Hello, I am Gaurav Dotto, and in this project, my task is to build a multi-thread code of 2D XY model. I have divided the task of energy calculation of spin configuration into different threads, but have kept other parts sequential as it is. So I did not use multi-threads to parallelize Metropolis algorithm application part. In my first slide, I have given a task showing running time of sequential code and its multi-thread version for constant step size, but with other but with different array size up to 1000 cross 1000, and this is the actual my slide. And in the second slide, i compare I compared the sequential timing and the parallel code timings with different steps. When I kept constant, then grid size 100 cross 100, and but they are not giving any effective speed up as compared to the first slide because I parallelize energy function, not the energy steps calculation. In my third slide, I presented plot between speed up and the grid size at constant 8,000 steps, which saturates when we increase array size. In my fourth slide, I show validation curve of my multi-threading and sequential curve. In my fifth slide, I gave equilibrium spin configuration at two different temperatures at T equal to 0.02 Kelvin and T equal to 10 Kelvin. And in my validation curve, I will give the two temperature validation curve. Means I give the for two different temperature, I plot the two validation curve. One for 30 cross 30 grid size at T equal to 0.05 Kelvin, and the another is 10 cross 10 grid size and T equal to 0.07 Kelvin. From the spin configuration, I will tell that at low temperature T equal to 0.02 Kelvin, they are actually forming the vortex formation and anti-vortex formation, where the vortex is the region in which spins swirl around a point, but in anti-vortex region they are actually rotate or curl around a point in the opposite direction. But in the T equal to 10 Kelvin, or means at higher temperature, vortex, anti-vortex, they are absent. And in my next two graph, I show magnetization versus temperature and energy versus temperature graph. But this is a qualitative agreement because my friend Amit, he uh, he presented the actual graph with large time. Because of time consuming, I just showed it via qualitative argument. Means I use 1000 steps and 6 cross 6 array size just to show that this is actually in agreement with my friend's result. And then I give the heat capacity versus temperature graph, and which has a feature at it is a maximum at T equal to Tc temperature, after which the phase transition occurred. And in my next slide, I gave the physical interpretation of the whole process. And there is phase transition. Then um, and now I explain the physical interpretation. There is a phase transition of lattice system at T equal to Tc temperature with respect to spin correlation function. Correlation decays like a power law function and at T less than Tc temperature, but at the higher temperature it decays exponentially. So at low temperature, the low temperature vortex anti-vortex are formed, and due to this the magnetization is very high at low temperature, as you see in my magnetization versus temperature graph. But as as long as the temperature is increasing, the vortex anti-vortex there disappear, and so they disappear, and the spin is randomized. So um, the spin is randomized, and the magnetization is very small. This is tends to zero, and the exactly graph as we find in my presentation. And and there is also a physical interpretation of this, that according to Manin-Wegner theorem, though average value of magnetization vector are always zero, and all as well as the average value of the spin vector, but at any finite temperature. But there will be a phase transition from quasi long range order to disordered phase for increasing temperature. For that reason, that type of magnetization versus temperature graph, as well as heat capacity versus temperature graph.
Hello, I am Kuldeep. I am doing CUDA version of the sequential code. Let's first see the speed up. I have run the program for fixed steps 10 to the power 4 and I increase the grid size. First I saw the timing in Python and C with the fast optimization flag. We saw the speed at 400 1000 into 1000, I get the speed up with respect to Python is 64 times, and with respect to C, 36 times. Now we fix the grid size and increase the steps. We can see that we do not get as such speed up because we parallelize the code in calculation in grids, not in steps. So we get more speed up when we increase the grid and fix the steps. Now let's say system of 32 into 32 dimension, and we run the Metropolis algorithm for 1 lakh steps. We run the Metropolis algorithm for two temperature, for lower temperature zero point 0.2 Kelvin and for higher temperature 8 Kelvin. We saw that after 1 lakh steps for higher temperature, the spins remain random, as you can see in picture, and for lower temperature, the system follows a structure. These structures are called the vertices and anti-vertices. At lower temperature, the system follows vertices and anti-vertices. As we go at higher temperature, due to the thermal fluctuation, the vertices anti-vertices pair is unbounded, so we didn't get any structure. Here I plot the energy versus steps graph for higher temperature and for lower temperature. I saw that for higher temperature the energy is fluctuating around zero and magnetization is zero, but for the lower temperature energy goes lowering by step. For and after 1 lakh steps the system goes into equilibrium. Now I plot the temperature versus energy graph and temperature versus capacity graph. We saw that with increasing temperature, the equilibrium energy is increasing. And for the heat capacity, we get a peak in the heat capacity versus temperature graph. This peak is around 1.75 Kelvin. And from this peak, we can say this is the critical temperature. And so we can conclude that by keeping step 6 and grid increasing grid size, we get a speed up in CUDA and heat capacity get 1.75 peak heat capacity peak. We get heat capacity peak at 1.75 Kelvin. So we can show that system goes a we have shown that system goes from order state to disorder state and vice versa. So we can say that system changes its goes through a phase transition from order state to disorder phase. Thank you.